Okie dokie. Right. Okay. Oh yeah. Assignment 4. No. Assignment. Okay. So topic 8 was the last thing we were talking about, was our linked stack. And we implemented that. We had our node class and we had our linked stack. We wrote our push, which was just adding to the front of a link structure, pop, removing from the front of the link structure, peek, not even removing, just return the data from the top, and then is empty in size. Raise your hand if you prefer the linked structures implementation over the arrays. I'm curious. And leave your hand up. I want to get a sense. Okay, you know what? Here, put your hands down. Let's do a vote. I want to actually do a vote. Multiple choice. Okay, start. There. Now vote. Oh, it's tight. Look at this. It's tight. Yeah, there is no expand capacity. We're still trying to understand. You can hear now. Well, that's good. Okay, so it's pretty tight. 5 people didn't respond, and a bunch of the people who aren't here restarted PC did it. Well, that's good. Okay, so it's still about split. All right, that's interesting. Very interesting. Which one do I like better? Oh, we'll find out. The one thing I didn't implement was the toString. Here's an example of a toString right here we could include, but I didn't write it in mine just because I'm lazy here. But one thing I do want to show you. So of course you can go, if you scroll down to the bottom, and I do recommend you work through this by actually playing with the tests, just for experience with unit tests. We won't do this together, but if you go, actually no, I will do this one with you. But one thing I want to do is if you go to here, there's an aside on nested classes. And then you can download the LinkStack code in the LinkStackTest. And then there's a more thorough version of a test. One thing I want to show you, the assignments. Oops. Come on. Is if we go and look at our linked stack, linked stack. If we look at the bottom of the link stack you can download, well, first of all, you'll see, okay, there's a toString there, but there's also an equals and a hash code. I've included the equals and hash codes in these collections for you because writing equals and hash codes for these collections are really challenging. So I've done it for you. I hear a boop. What does a hash code do? Very interesting question. I won't go into all of the details because it's a little bit outside the scope of the course. But you know how we were able to use maps? You know how like in assignment 1, you used a map to hold on to, did you? Well, in assignment 2, you're going to use like maps and sets and whatnot. And do you remember dictionaries in Python? So you did use hash maps. Okay, cool. The way that you actually get hash map versus hash code, yes. So you use the hash code is used for making the hash map. So if you want to put something in a hash map or a hash set or something, or even just thinking back to Python, if you want to put something in a dictionary, it has to have a defined hash code for that object. So we write them such that every instance should be unique enough that they can go into this hash set without any like collisions or all these extra fancy words that we would learn about like next year. But it's an important piece in order to use sets and hash maps and whatnot, because it's how they work under the hood. It's an interesting question, but the easy way around writing them is to just offload So if I want the hash code for this linked stack, well, I get the hash code of the size, I get the current, and then I take the hash code of each node's data and add it to the result. And then when I'm done there, so I basically hashed everything individually in this linked structure and then returned the result. This is not something you need to worry about too much, okay? It's just someone asked about like what's hash code. It's something important. You can learn up, you can read up all about it. It's really interesting, but not critically important right now. But, oh, boop. There is a hash code in assignment 2. Yes, there is. It should be the hash code if you go look at array stack. Yeah, here's the hash code there, along with an equals that's already there. Well, I'm not sure, but you know what? We'll move past the hash code stuff right now. But back to the linked stack. So we've got our toString, our equals, and our hash code. But I actually wrote a new class. But what you might find kind of funny is, well, hold on. I'm writing a class here, public class linked stack implements stack. And here's the open squiggle, and there's the close squiggle. But inside of it, we have a class defined inside a class, which is kind of weird. We haven't seen this yet, and it might feel a little weird. But what it basically private static class node of type T. This is basically the node class minus one of the constructors I had, right? If we go look at the node, it's the same thing. It's the same simple little class, but because the link structure, because the nodes is an integral part of the link structure, and it's only used for this linked structure, we'll define the node inside this class. So we make the node class inside this class as a way to just be like, yeah, okay, like it exists. I don't need these nodes elsewhere. And even if I did need nodes elsewhere, I might need a different kind of node. So I write the node inside this class. So everything inside the link stack is aware of node objects, but outside of the link stack, we don't care about them because it's not, the array stack doesn't care about nodes, right? But the link stack does. So that's the idea there. This isn't a like, oh, it's more correct to do it this way. If you don't like the inner class, you can have it as like, a regular old class node. But it's kind of like a design choice to make it, it kind of helps with code organization. So there's an interesting thing there. Tests. So I wanted to talk a little bit about the linked stack test. So testing linked stack. So to ensure correctness, we want to test with JUnit. If you have not, read the testing aside, which of course you all have done. So, and here also, there's an aside, a topic 8 aside on nested node class. It kind of motivates a little bit and explains what's going on. So if you're really interested, have a look there. I recommend it. But testing the linked stack. Okay, great. Let's test it. There's unit tests. All the tests will be the same in the array stack, except we don't need to check the expand capacity because it's not a thing in LinkStack. So let's go and look at each of these unit tests here. There's not a lot. This is a simple version. There is a more thorough version, linked stack thorough test, if you want to have a look. A little bit more detailed. We kind of talked about this in office hours today, actually. Some people were asking. The linked stack thorough might look intimidating if you go look at the linked stack thorough, which if you scroll down to the bottom, there's a download link to it. LinkStack Thorough might feel intimidating, but you might actually find it to be a little easier to follow despite the newness of things in there, just because it's much better organized. But we'll stick with the simple ones right now. LinkStackTest. Okay, what do I want to check? Well, a new stack is empty. If I make a new stack, it better be empty. So what am I going to do? Well, make a new stack, and then assert that when I say stack is empty, assert that it's true. If I make a new stack and is empty returns false, we got a problem, right? Empty stack has size 0. Okay, make a new stack. Check that its size is in fact 0. If it's not, if we make a new stack with nothing in it and it says its size is something that other than 0, we got a problem. Non-empty stack is empty returns false. Well, if we make a stack, we add something to it, is empty should be false. Pushing items updates size. I push 2 things. Assert equals size is 2. Good. Push item is top of stack. We push something on the stack. We want to peek and check is the top 99. Pushing and popping returns elements in last in first out order. Here's just a loop with some asserts in there. And pop throws no such element. There, cool. So just a couple of things that we're testing. So I can come here, I can go here, I can run the unit tests, and I can see, oh, look, they all pass. Oh, one test passed. No. There. 8 tests passed. They all passed. Yay. That's good. But, so, if someone comes along, though, and makes a mistake, so let's say your code, it's working, it's great, and then one of your colleagues comes along, and they're like, yeah, I'm just going to make some changes to the link stack. I heard of something that's really good. I'm just going to make some quick changes. And you're like, okay, great. They make the link stack, but for some reason, they accidentally forgot to update the size whenever they pushed and popped. They made a whole bunch of changes that you didn't see, but they forgot to increment and decrease size. Meaning that that stack is broken now. But okay, whatever. They made their changes. Then after their changes, I'm going to run my unit tests. And if everything passes, then I know that the changes they made are probably fine. But if I run my unit tests and I see, uh-oh, we're getting a no such element exception, pushing items update size is empty as fault. Like, we got a problem. So suddenly, oh, I know something went wrong in that last update. So I can go back and go, oh, that stupid coworker. Look, they forgot about size. So let's go back. I fixed their changes. I rerun the unit tests and, oh, they all pass. Okay, crisis averted. Cool. So yeah, there was some testing linked stacks. Any questions before we start talking about algorithm analysis, which looks like it's a long topic, but there's a lot of pictures, so it's not actually that bad. Any questions? All right, I'll carry on then. Okay, so this is a common question that's come up already. And it's good that it's come up already because it shows that you're thinking and your head's in the right place. What does it mean for an algorithm to be good? What makes one algorithm for solving a problem better than another? Because you've heard me say a bunch of times, there's an infinite number of ways to solve a problem, and they might all be entirely correct. But just because there's an infinite number of ways doesn't mean they're all good, right? Like they're correct, but are they good? Is one better than the other? Is one correct, but maybe it's not practical? So these are questions that computer scientists love to geek out about, and they can be answered in many ways. But one important measure is how much resources does your algorithm need? And there are a couple of key features of there are a couple key resources that we care about. The computation time. And when I say computation time, I don't mean like start the timer, stop the timer, but like the computational time. How much memory does it need? How many processors does it need? And how does the amount of resources that we're using change relative to the input size? This is going back to that idea of linear search. Remember how I say, if you're doing a linear search and you have n things in that list, how much work do you have to do? How many things do you have to look at to guarantee that you find the thing if it's in there? Well, you got to look at all n of them. Okay, if you double n, how much more work do you have to do? Well, twice as much. So as I doubled the input size, I doubled the total amount of work needed. Sometimes that relationship doesn't hold. Sometimes if you double the amount of work, you have a quadratic relationship. Or maybe it makes no difference at all, right? So it's kind of neat, but we're going to talk about all these things. So the above considerations are all important, but the big one we like to focus on, especially when we start learning about this, is time complexity. And this is what we're going to be learning about today. So we analyze the amount of time the algorithm needs relative to an input size. So how long does it take to sort 10 items? How long does it take to sort 10,000 items? And obviously it's going to take longer to sort 10,000 items, but like, can we understand how much more work it's going to need mathematically? This is one of the topics that when you start learning about as a computer scientist, if you're taking computer science because you're like, yeah, I kind of like math, but I hate math, but I like this computer stuff. And now you hear me talking about math stuff and you're thinking, oh boy, this is... So not only is this relatively simple math, but this computer scientist made it even simpler. So just bear with me. Because the computer scientists, remember, we're lazy. We don't want to think too hard. So don't panic if the math starts to get to you, because it'll even get cleaner as we go along. All right, we also like to consider the number of operations needed for an algorithm and the time complexity of those operations. Okay, addition comparisons. When we have a better understanding of our algorithm's time complexity, it can help us choose the right tool for the job. So this goes to the question of which stack is better, an array stack or a link stack? Well, an array stack might be better in this case, but worse in that case. But a link stack might be better in this place, but not in that place. It all depends on how you implement it. Worst case scenario, you can probably program a calculator to do the math for you. Yeah, but you'll see how easy it is. All right. Growth function. This is the big thing here. All right. This is the big idea that we are going to greatly simplify throughout this topic. So we want to understand the relationship between the size of the input n and the time it takes to run the algorithm. Can we use both type of stack in a... I mean, you would just need two reference variables for the two different stacks. And then you could actually like run them alongside each other and time their differences if you want to get like a stopwatch difference. But that's not the type of things we care about in terms of like time complexity, computational complexity. In practice, runtimes matter, but that's not what we're talking about here. Because we care about the growth function. It's not about how long something's going to take to run. It's more about how long something's going to need to take to run, how the amount of time it takes for something to run changes as the input size changes. Okay, we want to understand the relationship between size of the input n and the time it takes to run the algorithm, t of n. So we have some function, t of n, that if I know this function and I plug in, well, I have the input size of 1,000, it's going to tell me, well, the amount of time, the computation, the result is some value, okay? So the size of the input could be the length of the list sorted, for example. And how does the time to run algorithm t of n change as n changes? So we call this the growth function. Notice how t of n is a function of n. This means the amount of time needed depends on n. Remember, these aren't absolute run times. These are how long is it going to take on some arbitrary input size of size n? And how does that change as n changes? This is the key thing I want to emphasize, because a lot of people, when they learn this the first time, kind of miss that. So I like to emphasize it a lot. So here is an arbitrary growth function. At this stage, do not ask me where I got it or how it was derived, because it doesn't matter. Let's say I show up and I say, here is a growth function, okay? T of n equals 15 times n squared plus 25n. So if you come along and you have an input size of some value, you plug that in, you get the calculation, and then you know the runtime. You know the result of t of n, of the growth function. Again, don't worry about where these came from. So here's a table. And I've broken the this cost function down into two parts. The one with the n squared and the one with just the n. And then the total combined. And I've got n here. As if n's 1, well, this part is 15 times 1 squared. Well, that's just 15. The 45n, 25n. Okay, that's a typo. Here, someone go do a quick issue or submit a PR to fix this, because that's an issue. That should say 45n. Let's say, pretend it says 45n. 1 times 45, well, that's 45. And the sum of these two things, well, that's just 60. If n is 2, well, 2 squared, that's 4, times 15, that's 60. And then 2 times 45, well, that's 90. There we go. But as we go, as n gets bigger and bigger and bigger and bigger, like look, once I hit 1, 2, 5, 10, I'm going up by orders of magnitude. I'm multiplying everything by 10 as we go. Look at these numbers here for a second. Here, do I say, this table shows how each part of the t of n growth function changes. Take note of which part can be blamed for most of the whole t of n. Look at this table. We broke this function down into its two parts, the 15n squared part plus 45n. That's the whole thing, but we like to think of it as these two separate parts, 15n squared, 45n. If you look at the total amount of work needed, which of the two parts make up most of the work? The 15n squared or the 45n? The n squared part, yeah. Yeah, 15n squared, because look, here, calc. If I have 15, okay, hold on. Let's do 1 million, 1, 0, 0, 0, 0, 0, 0, squared times 15. Okay. Nope, no, minus 15 times 15. Okay. So there's this. Okay, so if I copy this, and then I know, okay, 45 times a million, that's 45 million. So 45, 0, 0, 0, 0, 0, 0, divided by that. I mean, the 45n squared makes up so 0.0003% of the total amount of work. And what's even more interesting is this gets worse and worse. As n gets bigger, that proportion is going to get smaller. Let's see what happens if I do like 10 million. No, I'll do a billion. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's a billion, right? Squared, because that's going to be a big number. Okay, and then 45 billion, 45, 0, 0, 0, 0, 0, 0, 0, 0, 0, 45 billion. Divided by that. Oh, I forgot to multiply that by 15. So I'll just divide that by 15. We get, okay, 0.00000000. What I'm showing you is the proportion of the total, the 15n squared plus 45n, of the n squared makes up so much more. And as n gets bigger and bigger and bigger, it takes up more and more and more and more of the total amount of work. The 45n starts to like just feign out into nothingness. It becomes like meaningless in terms of the total amount of work being done. And when this happens, I would say that this 15n squared part is the dominant part of this whole function of the t of n. Because the blame game would go to the part of the method, part of the code that is this 15n squared. Okay, so this table shows each part of gross change. Take note as to which part can be blamed for most of the whole t of n, the n squared part. When n is small, which part of the expression gives a larger value? Well, interestingly enough, the 45n, just as a consequence of the coefficient. But as n starts to grow, it doesn't matter. I mean, how much do the constants... Oh, okay, and here's another question. So we saw that the n squared part really matters. How much do these constants matter? the 45 and the 15. How much of an impact does it make? I mean, sure, it's 15, but like the 15 doesn't really have an effect on how, like, the magnitude of n when you're talking about n squared. Yeah, the constants barely do anything. In web and game development, since load and runtimes are so important, are Nsquared algorithms a no-no? That's an interesting question that I'm not sure how to answer because there's a lot of nuance I'd have to tease out of it. In game development, load and runtimes, well, load times are usually caused by, like, that could be a hardware thing. Runtime's important. N squared's not even that bad. But I mean, if you have an algorithm, it's not about like, oh, an n squared algorithm is bad. It's an n squared algorithm would be bad when there is an easy alternative solution to your problem that is linear, for example. What is a primitive type? Is that just a thing? Yeah. But whatever n has, yeah, primitive type, that's like int, double, Boolean, char. But of course they have their object versions like integer, double, character, Boolean. Okay, well, if you're getting that error, that's not really on topic. Let's try to avoid those types of questions. Okay, here, and look, okay, here. I'm plotting 15 n squared, 45 n, and 15 n squared plus 45 n. Look. This is how it's changing as n increases. But look, the 45n, which is linear, right? Like if you drew this on a graph, like an XY graph, it would just be a perfectly diagonal line. But of course, these scales are not matched at all. The n squared part dominates the 45n so much that the 45n is it looks linear. It looks linear. It looks like a straight line. It looks like it's not even changing. Like if you plot a constant, right, you would see this like flat line, right? So it's almost like this thing that's linear compared to the thing that's quadratic, the n squared, looks constant, looks flat. And you can't really tell, no, come on, because they're right on top of each other. Whoop. But the difference between the 15n squared and 15n squared plus 45n at these scale, you can't even tell the difference. The green line completely covers the blue line. They're the same line because the 45n is so meaningless in the whole shape of this growth function. If t of n is all this, 45n means so little in the grand scheme of things that, yeah, it's funny how it seems like so useless or not that important. So this plot compares the parts of the function to the function itself. Notice the scale of the axes, yeah. See how the part that grows linearly appears to be a horizontal line. Yeah, okay, yeah, I just said all that. Okay, warning. I hear a boop. What are the x and y axes? X would be the input size. So this would be like n, and this would be t of n. You're right, they're not labeled, so this is terrible graph. Okay, warning. This is to re-emphasize. One thing students tend to miss when first learning about computational complexity is that the function tells us how things change relative to n, okay? At this stage, we're not worrying about any absolute values here. So like if I give you this growth function, you may say like, okay, look at that thing. T of n, n squared plus 999 times n. Obviously the 999 n part of the function is going to dominate for all values less than 999. But that's not the point of complexity analysis. The point is identifying which part of the growth function grows faster. And in this example, the n squared absolutely grows way faster. We're not looking at this for any particular value of n. I'm looking at how it changes, like the plot of like, well, when n changes, how does it affect t of n? I'm looking at them as a function, no like single hard value here. So I want to plot this and not just be like, well, let's calculate it at a specific value, because then I would be like, okay, we'll just plug it in at 6,000 and I get this specific value. Great, but I want to know how it changes as n grows. So we like to plot these as functions. This is not to suggest that the observation of n less than 999 is not important or valuable. It's only to highlight that it's about change and growth. Okay. Questions at this point. We've barely scratched the surface, so there's probably a lot of questions. The one thing I want to note is, so far this is the summary. We have some growth function that is incorrect here, because that should say 45. Some growth function t of n, where n is the input size, and t of n is some function that if I plug in the n, the value of n, I get a number back. Great. And I also don't really care about it at any specific value of n. I care about it as a function. We also saw, though, that, we've got this whole function here, but really, we could break it down into parts and see that, well, this n squared part is definitely way more, like if we're playing the blame game for who accounts for most of the value of t of n, it's going to be 15n squared, especially as n gets bigger and bigger and bigger and bigger and bigger. Okay. So, asymptotic growth and big O. Here's how the computer scientists are simplifying things. And we're not even cheating. Like, this is all mathematically sound. But here's what we're going to do. We don't care about constants. They don't matter. We do not care about non-dominant terms. And what we do care about is asymptotic complexity, which is a fancy way of saying the time this algorithm takes as a function of n will grow like the function, and we like to pick a nice set of fairly straightforward functions to choose from. There are a lot more than the ones we're going to talk about, but the typical ones you're going to see, especially at this stage, are going to be constant time, log n, log base 2 of n times log n, and then n squared, n cubed, and so on and so on and so on. Don't worry about memorizing those couple things I just said. That's not important right now. But what we want to do is we want to take any t of n we get and boil it down into something that's like, hey, this t of n here that equals 15n squared plus 45, I would say, that function, it grows like n squared. So I would summarize that whole chunk of code that has this t of n of 15n squared plus 45n as just like, it's like n squared. So we say this has the big O of n squared. We care about the order of the algorithm. So let's talk about some example growth functions. If I have t of n is 17, this right here, let me put it this way, because remember, it's always about as n grows. How does the amount of work this function needs to compute? So how does the value of t of n change as n gets bigger and bigger and bigger and bigger and bigger? It's kind of a trick question. It doesn't. Correct. It doesn't. T of n of, let's plug in n is 0. All right, t of 0 equals 17. All right. Let's make n a billion. T of a billion equals, 17. Great. This algorithm, it's constant time. The size of the input, n, has no bearing on how much work it takes. And we're going to see functions that are like this. Here's one. T of n equals 20n minus 4. Well, this is a constant, right? For which, I don't really care about. And, sometimes, too, we like to think of these as, like, this is 17 times 1, where 17 is, like, the coefficient. So 20n minus 4 times n to the 0. I mean, I'm correct. It's it might be a silly way to think about it, but 4, it's a constant. I don't care about it. We ignore it. So it's 20 times n is the dominant part. But again, 20 is a coefficient. And I don't care about the coefficient because the coefficient there is just scales the shape. It scales linearly the shape of the function. It scales linearly the function, but the function still has the same shape. If I plot, let me be clear. I'm wording this poorly. Plot x equals y and no. Y equals x and y equals 20 times x. So you're going to be like, well, hey, look, obviously the one that's 20 times x, I realize this is here. This is kind of not that easy to see. You can be like, well, yeah, the thing, though, that's 20 times x, man, the scale makes this difficult. There, okay. So the scale makes this difficult to see. You know what? Let's make it a little easier. I'm just going to make it times 2, just to give you a better sense. So here's y equals x versus y equals 2 times x. This function's shape it's a straight line. Okay? This function, the red ones, its shape is a straight line. The only difference is its slope. So the coefficient scales it. It's a scalar. It scales where it is, but at the end of the day, the function is still a straight line. That's what I mean by like the coefficients don't matter. So if I see something that's 20 times n minus 4, that's big O of n. Ooh, this is a tough one. 12n times log base 2 of n plus 100n. Okay, so this here, log n is less than n. Okay, if I plot log base 2 of n, let's do that. Plot and y equals log base 2 of x. Perfect. Right? So we can see that the linear one here, this is the x equals y, you know, that grows linearly, which is fantastic. A linear algorithm is a great algorithm. But if you have something that grows log base 2, this is how it grows, meaning that it actually grows a lot slower than the linear. But it's still growing, right? It's not constant or anything, but it does grow a lot slower than linear. So log base 2 of x still grows, but it's definitely not as bad as linear. Is there infinity computers also, would a constant or a lesser variable that matches the capacity of your computer be important? Let's circle, okay, is there infinity in computers? Depending on how you interpret your question, see, you guys are asking good questions, but I don't know where the questions are coming from because I don't know if the question you're asking is as deep as it could be or because, okay, well, no, there is a finite amount of space on your computer, right? So there isn't infinity. But in computing, when we talk about computation, we do use the idea of infinity. So there's an inherent limitation of these computing machines. Would a constant or a lesser variable that matches the capacity of your computer be important? Yes, but, well, no. Infinity isn't a theory, but it isn't a number. Infinity is more of like an idea that says like, well, it just goes on forever, right? So don't think of like infinity as a number. Yeah, it's a concept. Yeah, there you go. But a constant that matches the capacity of your computer, is that going to be important? I mean, it could be, but the constant you're going to need is going to be just hilariously large that it's not going to matter. So I wouldn't worry about that. But getting back to this. Okay, so where am I going here? if I have, okay, look, this 12, we throw away the 12. So I'm looking at log times log n plus 100n. Throw away the 100. So I have n log n versus n. Well, linear versus something that's linear times log base 2 of n is going to be like log base n log n is going to be worse than linear on its own. And let me just show you that. And y equals x times log base 2 of x. There. All right. So log base 2 is the red one. Linear is the blue one. And yellow is the n times log base 2 of n. Or x, whatever. Which is pretty cool. And before you get too excited and you're like, wait a minute, we can go back in time. Well, no, because it's not, it's at 0 or 1. You don't have real numbers here. So don't get too excited. We can't go back in time. Okay. So n squared plus n minus 2. N squared. Why? It's the dominant term. I look at the exponents. Ooh, 2 to the n versus 3n? 2 to the n. 2 to the n is horrendous. 2 to the n is terrible. It's like one of the worst there is. We will look at an algorithm that is 2 to the n. But if you have an algorithm that's 2 to the n, give up. Go home. And yeah, here's some plots of how they look. N log n, which is better than n squared, but worse than n, and n squared is better than n cubed, but it's worse than n log n, and it just gives you an idea of where they look. Can we have n to the n? I'm sure you could, but don't. Why is this blue? Oh, we often try to keep the expression in big O notation simple. Here's a Wikipedia article about the common ones. Realistically, these aren't even the common ones. The common ones you're looking at are constant, log n, n to the power, linear, n log n squared, n to some arbitrary power, and then we're talking about like c to the n or n factorial. N factorial is real bad. Yeah, don't look at any of them except this one, 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 and this one. So just no. 1, 2, 3, 4. I'm going to combine these. 3, 4. They're the same. 1, 2. Realistically, you could also ignore these because they're terrible. Like but 1, 2, 3, 4, 5, 6, 7. Out of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See? Okay. All right. Oh, so let's test you. All right. This is big O of what? Someone say in the chat. N squared, yeah. Okay. N cubed plus log base 2 of n minus 4 is big O. N to the 3. There you go. I like the shift 3. 10 n log n plus 5. Ooh, not n. N log, 10 n log n. No, get rid of that 10. We don't care about coefficients. And no, not the log n. It's the n log n. They're multiplied together. If there was a plus between the 10n and the log n, the linear would be the worst one, but they're multiplied together. Okay, how about this? N squared plus n cubed plus 3. N cubed. N is bigger than log n, but this is n times log n. So if you take n, remember, the red is log n, the blue is linear, and then yellow is linear times log n. So yellow is worst of them. Would there be some problems that we wouldn't be able to solve with an algorithm that has a small order? We're going to get to these questions. That's a good question, and we are at a time, but you could make big money if you show up and solve a problem with an algorithm that beats everybody in any other implementation again. You could become a very rich person. No, the $1 million question is, I mean, you could interpret it as somewhat similar to this, but not quite. All right, we'll have to end here. Oh, no, we'll end on this last one. I know some people left, but only because it's the last one. 2 to the n plus 18n to the 100. Ooh. N to the 100 or 2 to the n? It's 2 to the n. 2 to the n is worse. N to the 100 is terrible, but 2 to the n we're scared of more. All right, we'll pick up at deriving growth functions next time. So basically, where the hell did I get that t of n from? All right, I'll see y'all later.